back. This time I'm going to explain you Lab 2. Today I'm going to explain you Lab 2 and 3 of this AMD FPGA Vivado flow, in which we perform synthesis and implementation using Vivado. In this lab, we take a Vivado design, convert it into hardware, and finally run it on FPGA basis 3 board. Our design is a UART based system. It takes input from keyboard, converts it into binary, displays it on LEDs of our FPGA board, and then there are some operations in it. If you press a button, it swaps the bits in it. This is the basic block diagram for lab 2. So basically, this lab demonstrates the design and implementation of a UART-based LED control system using Verilog and Vivado. The top module, this thing basically, the top module integrates multiple submodules, including a UART receiver, LED control logic, and metastability hardening blocks of reliable signal synchronization. The UART module receives serial data through the RX pin and converts it into parallel data. This data is then passed to the LED control module, which processes it and drives the LED outputs accordingly. To ensure stable operation across clock domains, metastability hardening modules are used for reset and button inputs. These modules synchronize asynchronous signals with the system clock, preventing unpredictable behavior. Overall, the design showcases how serial communication can be used to control hardware peripherals like LEDs, which also emphasizing proper while also emphasizing proper clock domain crossing and system reliability in digital system. So this was this diagram. Now moving on to lab 2. You can as shown in previous video for lab 1, you can read this document to get a detailed idea on how to do these things. After you do each of this step, uh, you will get something like this in Vivado. So to save time, I have already run the synthesis implementation in Bitstream. I'll just show you what the schematic looks like after running the synthesis, which is this. After implementation, the schematic will look something like this. And yeah, this. And then for Bitstream, I have already generated the Bitstream. What you have got to do is generate the .bit file, that is Bitstream, then open Hardware Manager, click on Auto Connect, then Program Device. Then that will be uploaded on FPGA, and now we'll move on to the demonstration. Hello everyone, this is our demonstration of Lab 2 and 3 for the Verilog HDL. So basically, what is happening here is that we are using a PuTTY software. When we type a character on the PuTTY software, so its ASCII value will be demonstrated on the basis 3 FPGA board. So we will begin by asking a question: what is a PuTTY software? So PuTTY software is basically, it acts like a serial console that allows the computer to talk to hardware using the UART protocol. So we know that the FPGA board does not have its built-in monitor or keyboard. So PuTTY provides the window where you can see the data FPGA is sending or receiving. So now the demonstration part. So when I press A, its ASCII value, its binary representation of the ASCII value will be done here. When I press B, it will be changed accordingly. When I press C, it will be changed. Now some of the numbers, 1, 2. Now in our project, there is a special board. There is a special button which you are using here, this one. So what will happen when I press the button? So when I press the button, it will perform the nibble exchange operation. Basically, the lower nibble and the higher nibble of the 8 bits will be exchanged. So what is a lower nibble? Lower nibble is basically the
Lower nibble is basically four consecutive bits which are ending at LSB, and the high nibble is basically four consecutive bits in a 8-bit string, 8-bit binary string starting from MSP. So the operation is like this. As you can see, the four first bits are swapped with the last four bits of the 8-bit binary string. So this is our lab 2 and 3, which is demonstrated successfully.